Coming up right now is the Space Show.
This is your community radio station, 88.3 Southern FM.
Welcome to the Space Show, presented by members of the Space Association of Australia. Hello, I'm Andrew Rennie, and on the panel we have Mission Control with Richard. And first up, we're going to have some space news. And here we go. I had written it down what we're going to do. Yes, some space news. And we're going to hear more from the International Astronautical Congress in Sydney. And we're going to turn back time to when one of our emissaries visited Pluto and, in particular, Arrokoth. But first up, Space Show News. AtSpace is a Brisbane-based rocket manufacturer. On November the 27th last year, they successfully launched their Australian-made A01 rocket from the Kuiper Test Range in South Australia. Launched at 9:22 a.m., the 12.2-metre tall rocket went higher than any other Australian commercial rocket has gone before. It went close to the target altitude of 80 kilometres. The 4.5-minute flight validated AtSpace's hybrid propulsion technology. Now, hybrid engines are ones that use a solid fuel and a liquid oxidizer. Because the Kuiper Test Range is an overland one, not an ocean range, the rocket could be recovered by helicopter for post-flight analysis. Otherwise, you've got to dig it deep out of the deep Southern Ocean. Now, to an astronomy satellite. In 2004, the NASA Swift satellite was launched into Earth orbit to detect the gamma ray bursts which come from the universe's most powerful explosions. In 2018, Swift was renamed the Neil Gehrels Swift Observatory in honour of scientist Neil Gehrels, who died in early 2017. Like all satellites in low Earth orbit, Swift suffers from atmospheric drag and has slowly been spiralling towards Earth. However, because of recent increases in the Sun's activity, Swift is experiencing increased drag. Rather than let the satellite re-enter the atmosphere and burn up, NASA has decided to contract Katalyst Space Technologies of Flagstaff, Arizona, to raise the orbit. And that Katalyst, by the way, is spelled with a K, not a C. Katalyst. A Katalyst robotic servicing spacecraft will rendezvous and dock with, then thrust Swift to a higher orbit. The reboost is planned for this southern autumn, and it lives in a few months' time. Well, that's our news on the Space Show. Now we're going to go off to the International Astronautical Congress in 2025, the opening ceremony. And we played some of this, I think it was last week. And now here's a little bit more of Australia's space history.
From the sound of the kookaburra to the vast silence of orbit, not many people from down under have risen above Earth's atmosphere. Paul Scully-Powers was our first. Andy Thomas was our most frequent. Chris Boshhuizen and Elaine Hyde went to space with Blue Origin, while Eric Phillips went from standing on Earth's poles to seeing them from space on the Fram-2 mission. Phil Chapman was a NASA scientist astronaut in the 1960s, but never flew. Megan Christian is a member of the European Space Agency Astronaut Reserve. And in 2024, Katherine Bennell-Pegg became the first qualified astronaut to represent Australia. While our mark may be small, it is growing. And there's now Aussie flags on the suits, inspiring a whole new generation.
Hi, I'm Paul Scully-Powers, and I was the first Australian to go to space. Before I really get started, though, I want to congratulate the IAC. When you think about it, it's a big auditorium. The escalator works. The teleprompter works. And the sound works. So almost 41 years ago to the day, I flew as a payload specialist on the Space Shuttle Challenger. And that was before the accident, I might add. I have been asked whether I flew before or after the accident, believe it or not. It was called Mission 41G, and I spent 8 days orbiting the Earth. But actually, and especially in America, I'm known for something which is more interesting than that. And that is, it turns out I'm the first person ever to launch into space with a beard. And I think to this day, I'm still the only person to launch into space with a beard. And there's a big story behind that, and I'm happy to tell you later. But before I was selected, I was working in the astronaut office in Houston. You've got to be in the right place at the right time. I was working for the US Navy at that time, and I was working as an oceanographer. So on my flight, it was the first space shuttle flight that was dedicated to Earth sciences, and that's how I got the gig. But I did oceanography from space, the first person to do that. And most people don't realise that the ocean is actually a heat sink, and the ocean drives the long-term weather. So one of the things that I was able to do is I discovered that many parts of the world's oceans have spiral eddies. And so their dynamics they're smaller than the big eddies you see in the atmosphere. But in a sense, they control a lot of what happens in the ocean. And the ocean controls the atmosphere and the long-term weather. So people don't realise that if we're ever going to get net zero, we've got to look at the ocean. And then my path to space was followed just 12 years later by Andy Thomas, who I think you all know. He became the first Australian national mission specialist in 1983. He made 4 space flights. His first in 1996, and he became the first Aussie to do a spacewalk in 2001. So here I am today. I relish my role as an advocate for Australia's sovereign space industries. And just before I finish, I want to give a shout out to Roger, who will be after Katherine. We all stand on the shoulders of giants, but Roger Franzen is a giant. He is the engineer who set up most of the space engineering in Australia, and you're about to hear from him. So once again, I'm Paul Scully-Powers. I'm part of Australia's space history. Thank you very much.
I'm Australian astronaut Katherine Bennell-Pegg. As a young girl, I looked up to giants like PSP and Andy, hoping with all my heart that I too would have the chance to be an astronaut. It at times seemed like an impossible dream. Australia didn't even have a space agency. So, like many of my era, I left Australia to pursue a space engineering career. But the establishment of the Australian Space Agency in 2018 brought me home, and others too, many of you in the audience today. In 2023, I began basic astronaut training at ESA's European Astronaut Centre, and last year I graduated as the first astronaut under the Australian flag, which I'm very proud to wear on my shoulder here. Thank you. Since then, I've been working with my colleagues to use the training to open doors for Australian scientists and engineers, and travelling around the country meeting young kids with that same wide-eyed optimism I had as a young girl here in Sydney, lying on the northern beaches, gazing up at the stars. And that is the power of space. And a dream. And I hope a reminder for all Aussies to strive for whatever their goal may be. I'm Catherine Bennell-Pegg, and I'm part of Australia's space history.
Aussie ingenuity is renowned around the world, and our space sector embodies that innovative spirit and creative problem solving. It's ingrained in our DNA. Across the 90s and 2000s, Australia used this spirit to carve out niches in space, working alongside our international partners like the US, Europe and Japan on combined ambitions and challenges.
The country's first satellite in more than 30 years.
Rode into space today on the back of a Japanese rocket, and scientists in Adelaide will use it for research.
From the Endeavour Space Telescope to FedSat, and the first ever IAC in Australia, the turn of the century was the spark before the flame.
Hello, I'm Roger Franzen, and I'm an engineer that's been part of the Australian space industry for nearly 40 years. I gained my early experience working in the United Kingdom and in Europe, and then I returned to Australia in late 1986, just as we were starting on a period of growth for the Australian space industry. I joined a company called AtSpace, which was Australia's premier space engineering company at that time. And then I became its CEO in 1998. Among the many projects that I worked on with the AusSpace team were the long-track scanning radiometers for the European Space Agency remote sensing satellites, the Endeavour ultraviolet space telescope that flew on the shuttle twice on STS-42 and STS-67, and Australia's centenary satellite, FedSat, that was launched in 2002 on the Japanese H-2A rocket. These were just some of the highlight examples of Australian space capability. That period has passed, but today we're seeing a new growth in sovereign Australian space capability, and I'm proud to still be part of it. My name is Roger Franzen, and I'm part of Australian space history.
And those comments from the opening ceremony of the International Astronautical Congress in Sydney. And many of those people have been on the space show. Now, another event at the Congress. In the Chang'e 6 mission was awarded the IAF World Space Award. This report from CGTN.
The global space community converged in Sydney on Monday as the International Astronautical Congress 2025 officially kicked off. During the opening ceremony, China's Chang'e 6 mission was presented the World Space Award in the team category, the International Astronautical Federation's highest honor for exceptional contributions. The award recognized the mission's unprecedented achievement, the world's first ever sample return from the far side of the moon. Mr. Hu Hao, chief designer of the Chang'e 6 mission, accepted the honor on behalf of his team.
We appreciate the international recognition of the Chang'e 6 mission. Advancing human well-being is our shared vision. Through the development of space technology, we hope to work hand in hand to create a brighter future for all.
In accepting the award, Hu highlighted why this project resonated strongly with the international community.
The Chang'e 6 mission marks the scientific precedent of retrieving far-side samples, which is vital for global lunar research. Meanwhile, the wide acknowledgement of our commitment to international cooperation, including the 4 international payloads, and third, the exceptional performance of our team in completing such a complex mission.
Beyond the engineering feat, the Chang'e 6 mission also explored a broad landscape of international cooperation, carrying 4 international payloads on board. Dr. Rahan Mahmood contributed to the payload from Pakistan.
And I'm very much excited that the Chang'e 6 got that award of IAF this year. And it is a very excitement moment that both of the countries put their effort and put one of a lunar CubeSat in the orbit, iCubeQ. I believe that in future a lot of collaborations will continue between China and Pakistan.
It was amazing to be at the opening ceremony and see that the Chang'e 6 mission was awarded. The collaboration that China has been offering is amazing, particularly to countries like South Africa. My organization, our payload is going with the Chang'e 8 mission. It was announced in April this year. It's a wonderful opportunity for us that we would not achieve without collaboration, and we're very proud to be a part of it.
Both near and far-side lunar samples brought back from China's missions are also exhibited at the event.
These unique samples are resulting in major scientific breakthroughs, unlocking the mysteries of the far side of the moon. This mission and this award underscores the sophisticated capabilities of China's lunar program and its commitment to contribute to humanity's shared knowledge. IAC CGTN, Sydney, Australia.
In other related news, researchers from Sun Yat-sen University in China have answered a long-standing question about the moon. Even a casual look at the lunar photographs show that there have been landslides, sometimes large ones. Most of these are thought to have happened billions of years ago. The question is, could landslides still happen today? The Chinese researchers analysed images of the moon taken at different times by orbiting spacecraft. They found landslides that had happened since 2009. These new landslides are shallow and small, each displacing less than 100,000 cubic metres of material. Most measure less than 1 kilometre in length and 100 metres in width. Fewer than 30% of the new landslides appeared to have been triggered by asteroid impacts, as judged by the proximity of new impact craters. The other 70% of landslides were caused by seismic activity. The location of the landslides provide an indicator of active seismic zones in the lunar crust. It also provides a strategy for placing future seismometers efficiently to better probe the moon's internal structure.
You're listening to 88.3 Southern FM, the sounds of the Bayside.
And now it's time to turn back time. Here on the Space Show, we like to celebrate anniversaries and multiples of 5 years, as near to the date as we can. But this year, as most years, we were doing science fiction in January. So we're going to be looking back 20 years to 2006, January the 19th, when the New Horizons spacecraft was launched on a journey to the dwarf planet Pluto and to any asteroid they could find out there. Well, Pluto flyby happened on 2015, July the 14th, past 12,500 kilometres away from the dwarf planet, and continued outwards. Then they discovered a Kuiper Belt object, an asteroid if you will, to fly by, and they did that on January the 1st of 2019. That was 6.5 billion kilometres away from the Sun, and the flyby was 3,500 kilometres away. Well, that was on January the 1st. Next day, there was a press conference held with the media, and we're going to play back the question and answer session from that. And the respondents are Alan Stern, Cathy Olkin, Carly Hallett, and Jeff Moore. So let's go to the press conference.
Hi, it's Bill Harwood, CBS News. For Jeff, looking at those pictures and looking at the neck specifically, is there any way to even guesstimate how strongly bound those two lobes are? I mean, it almost looks like you could break them apart pretty easily. I mean, is there any way to make even a guess at that? Thanks.
Well, that's a fair question. We think that they are, in a structural sense, soundly bound in the sense that you probably couldn't walk up and push them apart yourself. But they obviously came together at such a gentle speed, as I said, maybe a mile an hour or a few miles an hour, that they really are sort of resting on each other. You can kind of think of it as analogous to a spacecraft docking with another spacecraft, almost more than you can imagine it being any kind of collision.
And if I can add to that, we've already done the calculation to compare the centripetal force of that 15-hour period to the mutual gravity of these two lobes attracting one another, and shown that the mutual gravity is substantially larger. And so their gravity alone can hold them together, and even without any mechanical forces adding to that.
Okay, a question here in the auditorium.
Hi, Chris Lintott from BBC Sky at Night. Question for Carly. It looks like there's some colour variation in the image. Could you say something about how that might have happened, or rampantly speculate about what might have been going on?
So the two lobes, Ultima and Thule, do look the same within error, and so there's no variation significantly there. The big variation is on the with the neck region, and that's less blue. But at the moment, this is the first time we've processed it, so we'll be getting a lot more data soon, so we hope to be able to say something more about the small-scale colour variations in the next few months. But I think that's all we're willing to put money on right now.
I'd be curious to know what's the biggest surprise from what you've learned so far, and how much bigger do you think is Ultima versus Thule? It's hard to tell. Is it like 3 times the size, or maybe some scale references besides just the length?
Yeah, those are great questions, Marcia. And in fact, if you take their individual radii that we've now measured by fitting ellipses to the profiles of each of the two lobes, and then from that calculate their volumes, it is almost exactly 3-to-1, your guess, between the small one, Thule, and the larger one, Ultima. And you had another question? Surprises. Well, as the principal investigator, I'll say I'm surprised that more or less picking one Kuiper Belt object out of the hat, that we were able to get such a winner as this, that's going to revolutionize our knowledge of planetary science.
This is Leo Enright with Irish Television. Congratulations. I know, Alan, that Kenneth Edgeworth would be very proud of you today. But I have a question about this contact binary as it being the first. Was Churyumov-Gerasimenko also theorized perhaps to be a contact binary, or am I misunderstanding?
I think that, if I understand your question, is how common are contact binaries? Is that what he was asking? Let's say that was your question. Okay. As you say, a number of people have done studies to understand the evolution of features in the outer solar system, and it seems that contact binaries form commonly enough. It's interesting when you look at, for instance, comets that visit the inner solar system, which we've sent spacecraft now to several of them. They're quite commonly bilobed. Now, there's been a big controversy on how those lobes form. Are they entirely as sublimation features? Is that to say they're due to the evaporation away of the material which they're made of, or are they actually some sort of primordial shape which has been massively eroded? But anytime we see comets, we have to remember they're post-toasties. They've been, fried and crackled and crunched by the sun, and they're badly damaged examples of former Kuiper Belt objects. And so, being able to go out and see a pristine Kuiper Belt object tells us now that indeed contact binaries really do form, and maybe when we see comets, we're looking at smaller versions of very badly damaged contact binaries.
And if I can just add one thing, I think that this is the first object that we can clearly tell was born this way and didn't evolve to simply kind of look bilobed, that formed in this very gentle accretion environment that Jeff described, and that hasn't evolved in all this time, as we talked about in the pre-flyby briefings, because it's so small and so cold. And so this really puts the nail in the coffin now. We know that this is how these kinds of objects in many cases formed.
Okay, I believe we have a follow-up on the phone, too.
Yeah, thanks for clarifying that. My other question was to do with the comparison of redness between Charon's North Pole and this object. My understanding was that Charon had this color due to deposition from Pluto through some sort of complex interaction between the two bodies. So I'm wondering, does this make you wonder again about the origins of Charon's redness? Or can you even wildly speculate, to quote my colleague, about how you end up with such redness also on this body, which is completely away from any large object?
So we think that the color, while the coloration is similar, the color ratios are similar, the processing is different. We still think that Charon has this redness on the poles because it's sort of getting volatiles from Pluto's atmosphere that are kind of cold trapped on the surface of Charon, and that's clearly not the case on Ultima. I mean, there's probably something from the matter that it formed from that could have had those volatiles in, which have slowly been irradiated or from different maybe types of particles and changed. So the process by which it got red is sort of similar chemically, but that doesn't necessarily mean that the essence of that volatiles is the same. Does that answer your question? I think that's right.
I'd like to add to that.
Sure.
So there's many different ways to make red material, and the red material that we see on Mordor Macula in the North Pole of Charon, we have one explanation for how the volatiles got there and how they were processed. The volatiles escaped from Pluto, landed on Charon, became cold trapped, and were irradiated over time. That is consistent. The process that we were just talking about could be the same thing that happened on Ultima. There are also other processes, perhaps the smaller particles that then accreted into Ultima became red earlier. So organic material can appear red, and so there's a number of different ways of going at this.
Hi, this is Lisa Grossman from Science News. I have a question for Carly and a question for Jeff. For Carly, can you say more about those exotic ices? What do you think they are? And for Jeff, is the resolution good enough at this point to say anything about whether Ultima Thule has any craters at all? Is it lacking craters? Are they just very small? And what does that mean?
So this is Carly. I'll go first. So we don't really know. We think it might be methane. It might be nitrogen. We have LISA data coming down soon, and so we hope to be able to give you a definitive answer maybe by tomorrow, maybe later. So stay tuned.
And one word on the LISA data that's coming down. So there's data coming down right now. We had to bring down only selected wavelengths, so we will have some parts of that answer tomorrow, but it'll wait the full data downlink until we can get the full answer and be sensitive to all different species that we can look at in the infrared.
Okay, as I said earlier in this briefing, we've seen no unambiguous evidence for craters on the surface of Ultima Thule, but almost certainly I'd be surprised if there aren't at least a few. Now, theoretical study suggesting what the crater rate in this part of the solar system, the cold classicals, might be, suggests that Ultima Thule could be very underpopulated with small craters in comparison to, say, the asteroids or something in the inner solar system. So we may discover it doesn't have very many craters. In fact, we may very well find that most of the texture is dominated by, again, these very slow motion accretional processes, as opposed to the higher velocity processes which produce impact craters.
And I'd like to add, just to sharpen up so we don't get any misreporting due to our not being clear, we're not saying there aren't craters on Ultima or on Thule. What we're saying is the lighting geometry on approach with the sun behind the spacecraft's back makes it hard to see whether the features on the surface are craters or not. And as we fly around the side of Ultima, we'll get that view with what we call higher phase angles, which means more shadowing. And we'll be able to make a definitive determination, and ultimately we'll count the number of craters as a function of their size to understand the impactor environment. Unfortunately, the approach images that we're showing you that came down first just aren't conducive to determining whether there are craters on the surface or not.
Hi, Dave McDonald with The Sky this month.
realizing we do have 20 more months of data to come. But so far, do we have anything that would confirm or alter our thoughts about the formation of the solar system or planets in particular yet?
Well, it's actually gratifying to see these almost perfectly formed contact binaries in their native habitat. People have speculated for a long time that processes, such as the process that was illustrated by the sketches I showed you earlier this afternoon, might be how the initial primordial clumps come together to form the what's called planetesimals, which are the things which in turn go on to make the planets. But to actually see the things that in fact are consistent with the explanations that we have and theories we've had for how these things form was extremely gratifying. So to zeroth order, our ideas of how these things form seem to be somewhat vindicated by these observations. But of course, as was alluded to before, actually studying the details of how Ultima Thule is shaped and was formed will go very far to clarify the details of that formation processes.
All right, guys. Mark Strassman with CBS. I have a question about the pictures. Do we have a sense yet of how many there are in total? When and from how far away this one was taken? And then once we get closer, how distinctive will the topography become?
Okay, that's easy to answer. As Alan had just mentioned, that as we get closer and closer to the target, the sun illumination will change. Instead of having the sun shine straight onto the target like it is in the images we showed you today, the sun will be moving over to the side, and so you'll have lengthening shadows and hills and dales and craters if they're there. They'll begin to express themselves, and at several times higher resolution than you saw in the images that we displayed today. So the combination of higher resolution, much better lighting, and the fact that the presentation of Ultima Thule will change as the spacecraft flies past it will allow us to also generate very high resolution topographic maps. So we'll be able to tell you precisely about the shape and sizes and origins and processes which form the landscape.
And I just wanted to add some quantitative details there. So the highest resolution image that we showed today is about 140 meters per pixel. The slightly lower resolution is a little more than 300 meters per pixel, and our highest resolution that we will get down later, we don't have on the ground yet, is expected to be about 35 meters per pixel.
Yes, so what she said. But I'll just add, the current best picture that we have, I believe, has 20,000 pixels or 28,000 pixels on the target, which way beats the 6 pixels we showed you last time. Okay, we're in a different regime now. But ultimately, if everything worked just right in that stretch goal observation that we call CA06, or the Close Approach Observation 6, the highest resolution image set that we took, that Cathy was describing, that'll have 35 meter resolution, will ultimately be a megapixel image. So it's going to just get better and better. And in total, you asked about how many images. We take images different ways. We have the color and the panchromatic. And as we do the very close approach observations, we're going to be taking several dozen. If you add up all the various kinds of resolved imaging that we'll do, including the imaging for spectroscopy, where we actually map the surface composition at all these different wavelengths, there will be hundreds of images in the end. And I think we've got 4 on the ground, or possibly 3.
Stephen Young with Astronomy Now magazine. Your photos from the science team room showed us the excitement today. What's it going to be like tomorrow? And what missing parts of the puzzle that are coming down right now are you most looking forward to seeing?
Well, I think that each scientist on the team has their own biases as to what they're most looking forward to. Personally, and I think we'll just go right down the row and each person can speak to it. I'm looking for getting the satellite search results. You know, Jeff showed that swarm of objects that we think were the Ultima Thule system early on, and which ultimately coalesced into the 2 lobes. I'd like to know whether or not any of that material at all is orbiting, even as objects that are just 100 or 200 meters across. Cathy?
Yeah, thanks. I think the real excitement today is going to be in the composition theme team room. Right now, as we're speaking, data is streaming in on the LISA data, which gives us our composition information so we can map the surface composition. And we're all very interested, or maybe it's my own bias, but I'll say I'm very interested in understanding what the surface composition of this object is. There's no way to make anything like this type of observation without having a spacecraft there. It's why this exploration is so critical.
I share Cathy's bias. I'm excited for the composition coming down this afternoon. I'm also excited in the future to, of course, get high spatial resolution color. But yes, I think the excitement's with composition today.
Well, wearing my geology hat, I'm going to say, of course, what we're really interested in our group, the geology imaging group, is to take the images we already have on the ground, and we already have the first batch of images down, and we won't get additional images until about a week or so from now. So we're taking the images we do have, and as I mentioned earlier, the two images are taken at slightly different perspectives, and so by going back and forth between the perspectives, we can probably, using geometry or trigonometry, map out local highs and lows and get some understanding of if we're seeing craters or we're seeing hills. And that's going to be what we're really going to work on, be cranking on this afternoon and overnight, and hopefully we'll have a presentation for you on what we discover tomorrow afternoon.
On the Space Show, we are at a press conference with the findings of the flyby of the Kuiper Belt object, or asteroid if you prefer, Arrokoth. And we're going to be back, looking back in time after these messages.
Serving Bayside Melbourne for 35 years, this is 88.3 Southern FM.
On the Space Show, we are looking back in time to 2019. January the 1st was the flyby of Arrokoth, and the next day they were discussing it at the press conference. Let's go back to that press conference now.
Oh, hi. This is Dave Mosher. I'm a science and technology correspondent with Business Insider. I have a question about, firstly, what comes after this? Maybe it's a bit premature, but New Horizons is still moving along very quickly. Do you hope to reach another target, and approximately when? And then also, I understand you took some images from behind MU-69. What do you hope to get out of those images in its shadow? Do you hope to see an atmosphere? Do you expect that? And what might that tell you? Thank you.
Yeah, I'll take the first part, and somebody else can pick up the second part if they like, or I'll answer if nobody volunteers. I think the first part of your question was about, what was it about? I'm thinking of the second part.
Next target.
Yeah, the next target. That's easy. I love that subject. Yeah, so as background, New Horizons is a very healthy spacecraft. In fact, all the systems on board are redundant. And we're not using any of the backup systems because we've had systems failures, even though we're 13 years in flight. So spacecraft is in peak health. It has power on board the nuclear power generator to operate for between 15 and 20 more years, and therefore to travel out to about 2.5 times its current distance from the sun and explore much further. And we have the fuel to do that too. Now, the key to the science that we do is whether it's science studying objects remotely with our telescopes, or whether that science in the Kuiper Belt also will include one more flyby. And I can't give you the answer today because we don't know. We've been very careful during this period of 3 years where we were planning every detail of this flyby to stay focused on that and not get distracted by the next shiny thing, if you know what I mean. So, in fact, the Planetary Mission Senior Review will call for proposals in the summer of next year, 2020, and we'll propose to NASA an exciting program. And then if that proposal is accepted, we would start a search for an object that we could fly by. Now, the Kuiper Belt is vast. We're currently at 44 astronomical units from the sun, each of those being the distance from the Earth to the sun. So we're 44 times as far out as the Earth. And the extensions of the Kuiper Belt go out as far as about 70 astronomical units. And we won't be there for almost a decade. So there's plenty of time to go find other targets if we're in the position of having a still healthy spacecraft, an accepted proposal, and our search is successful. So stay tuned.
This is Kelly Beatty from Sky and Telescope. I am just amazed at these images. Can someone address, now that you know the shape and the rotation pole, what fraction of this you will not be able to see because it will be in shadow all the time, even as you get behind it?
So we know that the rotation pole is tilted about 30 degrees away from the line of sight between the spacecraft and Ultima. And so we're seeing a little bit more than half of the target as it rotates. We haven't seen all of that yet in high resolution, but we'll get that down as the days and months continue. But we're getting a little bit more than half.
Yeah, and I can tell you that on a flyby like this, when you don't know the rotation period in advance and you can't plan for that, you can't predict exactly what you're going to get. And now that we, in the last day or so, have got this roughly 15, 16-hour class rotation, we can tell that this is actually a pretty good case, and we're going to get more than the minimum by quite a bit. But we can't give you an exact number just now because the error bars on the rotation rate are still substantial enough that we can't get the precise number.
Just thought the panel might be amused to know that although you're comparing this to a snowman, the Twitter is also have concluded it's in fact BB-8. But its spherical shape has already struck me as a lot more spherical than what was predicted. And I'm wondering if that comes as a surprise to you, and does it suggest anything about its potential self-gravity?
You take that?
Yeah.
Okay. Well, yes, we were also surprised about how spherical the two lobes were, and we right away came to the conclusion they could only be explained by the aggregation or collection or slow coming together of numerous smaller objects, and basically it's an aggregate or accretional surface. And it's really hard to imagine how you could get a sphere by any other means other than through this slow collection of particles from some localized swarm. So to say it was unexpected might be false because we understood that if the situation I just described was in fact how these things form, they would in fact be spherical. So it confirms one of the several explanations or ideas people have on how planetesimals, the building blocks of planets, come together. I think that answers the question, I hope.
Yeah, I would just add that, this is how science works, is that the theorists have ideas, they do computer modeling, they think hard about problems, they take the available data, and different models produce different outcomes. But then you need more data in order to distinguish between those models. And in the last 36 hours, NASA and New Horizons have collected more data on the formation of the solar system, and particularly on planetesimals in the Kuiper Belt, that let us now choose between models, or at least be able to tell which models are more likely to be right than others.
And I'd like to add that, just a couple of days ago, we were talking about how we would learn about the solar system formation and evolution by looking at Ultima. And this bilobate shape is exactly what we were talking about. We didn't know what we would see, but this shape informs our models of planetary formation. You can see that they're clearly two separate objects that have come together. There's no strong neck in between each object, just like perhaps I postulated a few days ago. It's not there. It's okay. And so,
Do tweets count as publications now?
Yeah, right. So it's pretty exciting to see that. I think this is exactly what we need to move the modeling work on planetary formation forward, because we're seeing evidence right here for accreting objects and then having them combine.
Hi, Sarah Kaplan from the Washington Post. Kathy, I was hoping you could talk a bit about, since the geology is giving us these insights into sort of the physics of planetary formation, is the composition and the chemistry of the object, are there particular questions that you think that's going to help answer? And are you willing to speculate a little bit on what Ultima Thule might be made out of and what kinds of things we're going to learn tomorrow?
Yeah, so that's why I say I think the excitement will be in the comp room today, because we're getting that first data down that tells us about the composition of the surface. But the color also informs us about the composition of the surface. And so we see red areas and less red areas. And the red looks very indicative of tholins, processed volatile ices that have been irradiated by energetic flux, Lyman alpha radiation, gamma rays, the like. And so that's one way to make that red material that we see. And the less red neck area combined with the high albedo is consistent with fine-grained particles that have settled into that region because of both the slope and the gravity that you would get there. And so I think we are learning a lot about the composition of the surface and the particle sizes on the surface, but we really need to have the infrared imaging spectrometer data down on the ground, and I bet it's there now.
Hi, Jean-Luc Dauvergne for Ciel et Espace. It's a French astronomy magazine. When the probe was between Pluto and Ultima Thule, you have observed a lot of Kuiper Belt objects to study their roughness and their rotation period. What did you learn about that, and is that similar to what you have discovered on Ultima Thule? I mean, do you think that all these objects are similar, or do you see some differences between them?
Well, we obviously see some pretty dramatic differences between Pluto, which is the size of the United States, and Ultima, which is the size of a large metropolitan area, just in their basic makeup, and you can tell from their shape. Pluto is large enough to have crushed itself into what we call hydrostatic equilibrium. It's perfectly spherical, and Ultima has these two lobes that are individually sphere-ish, but as an object, you see it's bilobate. As we get higher resolution data and the composition data and the higher resolution color, we learn more about it. I predict that not only will Ultima's landforms and composition be very different from Pluto, but even from Pluto's small satellites that are of similar size, because they were almost certainly formed in a very, very different environment in a disk of material around Pluto that resulted from this giant impact that created the satellite system. If others want to add to that, please do.
Well, just to expand on your point that the small moons of Pluto resemble shards, like you find from a broken piece of pottery, whereas the Ultima Thule resembles two objects which came together and themselves each formed as purely accretional objects, not as fragmentary objects. And that's the fundamental difference between how the small moons of Pluto formed and how Ultima Thule and probably most, or at least very many, of the cold classicals have formed.
And then I'll also add that the 15-hour rotation period is a very typical rotation period. You don't need to come up with any odd explanations. Like if it were very, very fast, then you would have it rotating apart, and it could tear itself apart. That does not happen at 15 hours rotation period. And if it's very slow, then you need to figure out some way maybe that you could have slowed it down. So this is a very regular rotation period that we're seeing.
Bobby Russell with Quest for Stars. A question on the contact zone and the ice there. Would there be any way to derive from the team the internal composition of Ultima Thule from debris frozen in that ice or layering around the contact zone?
We're certainly going to look in any windows that are available to us. By windows, I mean fissures or craters or other windows into the interior where we can see evidence of what's going on in the interior in terms of, for example, layering, or color differences or composition differences that might exist. As far as the bulk density, because the objects aren't orbiting one another, because they're physically attached, and if we don't find any small satellites that were left over from the pebble accretion swarm, then unfortunately we're not going to be able to get the density of the pair directly. We can set some weak constraints on it from mathematical models, but we won't be able to actually measure it because Ultima is just too small for us to measure the bending of our spacecraft trajectory, which is microscopic at the distance that we flew by with present-day technology.
Hi, thanks. Ken Kramer, Space Up Close. I'm wondering also about the forces keeping it together and breaking it apart. You just mentioned a little bit about the question I had, the rotation. What kind of rotation period would you need to see for this to break apart? Well, and when will we see some data on whether there's any gas evolution? Thanks.
As far as the rotation rate, it depends upon several factors, like what are the densities of the two individual lobes, which we don't know. So we can't give you one answer for that, but we can produce models with curves that tell you for the different densities and for other assumptions what the critical speed is for the two to separate. Obviously, they're not doing that, so that provides a constraint for us. Our first calculation showed us what I said was a weak constraint because nobody expects a density this low, but the back of the envelope calculation was that for an assumption of 1 gram per cubic centimeter, basically a composition of water ice for the material, that the individual bodies can't be have a porosity that corresponds to a bulk density of less than about 0.2 grams per cubic centimeter. Hope that helped. What would the rotation period be? Oh, that's for the current rotation period. You'd have to spin them up to very fast rotation periods, like Jeff said, of 2 or 3 hours.
We actually looked at that when we were still trying to explore the rotation rate, which we only determined in the last day or two. So there was a possibility of a high rate rotation, and quickly did some back of the envelope calculations and determined that if we're going, say, 2 or 3 or 4 hours, it probably would fly apart. Since it didn't, now we know it's 15 hours, we're fine. But that answers your question, I hope.
And we were at the press conference that was announcing the results of the New Horizons flyby of the asteroid Arrokoth in the Kuiper Belt. And that happened on 2019. Well, I'm Andrew Rennie. This has been The Space Show. Thank you very, very much to Richard. He's done an excellent job here, even though you haven't heard his voice.